In this video, I'm going to be covering the covariance matrix, the correlation, and some associated things that you might want to know if you know about those two things. This video is intended for people who might have seen a covariance matrix in the context of a PCA or a linear regression or something like that, and just wanted to learn a little bit more about it. So these are the 8 topics that I'll be covering in the video that you're about to watch. I might put it in the show notes as well. If you have any errors that you would like to point out or any suggestions for things to do differently, then feel free to leave a comment on that. We're using D as our dependent variable and I1 and I2 as independent variables. Of course, you can plot your dependent and independent variables in R pretty easily in base R with the plot function, right? So on the x-axis, we're going to do, say, I1, and then on the y-axis, we'll do D. And unfortunately, it doesn't work when I have the screen recording software open, so it just gives me this error. But I promise it'll work on your computer if you just try this. But what does work, fortunately, is the Plotly libraries plotting function. So I'm just going to show that off real quick. So here we're going to call the Plotly function, and we're going to make the x-axis be I1, the y-axis be I2, and the z or z-axis be the dependent variable D. I'll just hit enter on that, and then make this large here. So you can see we got this nice 3D scatter plot here, and you can kind of rotate it around. Very fun stuff. And you can use it to look at projections of this data. So here we got the z-axis and the x-axis, although this is flipped, so I'll just flip it around here. So you can see as we increase in the x, we also increase in the z. So that's going to be important. And then similarly, if we increase in y, so we got lower y here, higher y over here, we're also going to see an increase in the z here as well. So the next important thing to talk about here is going to be the variance. So I'm just going to make that plot small again. So the variance is going to be the average squared distance from the mean of a variable in that variable. So we can get the mean of I1, and that is going to be 2.6. And so then we can also get a variance for I1 through the following formula. So I'll just paste this in here. So it's going to be the sum of the squared differences between that mean of I1 and I1, or the squared differences between I1 and the mean of I1, I should say, divided by the length of I1, so that's your sample size, minus 1, because in this case, dealing with a sample, not the overall population. So this is what I mean by an average of the squared distances, right? So we have this, the squared distances, we sum it up and we divide it by our sample size, and that's just an average, right? And so we can do this and we can get a variance for I1, and that's going to be 3.3. And so the variance is a very handy measure of how spread out the data is. And of course we can do that for all of our other vectors here as well. So for I2, for example, we can get 1.907, and then for our dependent variable D, we can get 2.214 or something. So yeah, the variance is a very handy measure of how spread out your data is, because it represents an average of the squared distances between your data and the mean of that data. So the next important thing on the list here is the covariance. So the variance, it tells you about the average squared distance from the mean in one variable, but only in that one variable. It doesn't tell you how these variables vary with each other, which is kind of what we're trying to look at with our 3D plot here, right? If we're saying, okay, so here, let me line it up. Here, if we see an increase in the x, then we see a corresponding increase in the y. This variance doesn't really tell us anything about that. And so that's the whole point of the covariance, right? So the covariance kind of answers this question of when one variable increases, what happens to other variables. And so the covariance is calculated between two different variables, not between many different variables. And it's calculated according to the following formula. It's going to look pretty familiar here. So we've got the sum of the distances between this variable and its mean multiplied by the distances between this other variable and its mean, and again divided by our sample size minus 1. And so this looks pretty familiar because up here you can see that this is squared. Our variances are always squared. And this one, you're just multiplying like the square root, I guess, or the distance between the variable and its mean by the other one, rather than just squaring this, for example. You're multiplying it by this other one. So that's why it's the covariance rather than the variance. So we can calculate that and hit enter. So this tells us that the covariance between I1, our independent variable number 1, and D, our dependent variable, is going to be 2.56. So really all we can gather from this, since this is positive, that means that these two variables are positively related to each other. So if D increases, then you would expect to see an increase in I1 as well. Beyond that, though, the covariance doesn't really tell you a whole lot about what your data really does. So the covariance is neat and all, but we want to be able to calculate this efficiently for all of our different comparisons that we're making in this case, because we have three different variables here. We have I1, we have D, and we have I2. So we want maybe a matrix-based solution to be able to efficiently calculate all of these covariances for each of our variables. So this right here, the sum of the element-wise products between this vector and this vector looks a lot like a dot product, or the product, the matrix vector product between the transpose of this vector here and this operator here, this percent asterisk percent is the R matrix multiplication operator. And then this vector here. And then again divided by the sample size minus 1. Parentheses. And so we get the same exact thing. And so this gives us a pretty easy starting point to be able to scale this up and do it on our entire data matrix. The dot product is also a really good way of understanding what the covariance is trying to tell us. So up top here I have the covariance of A and B, and I've expressed it two different ways, right? So up top you have the sum of the element-wise products of the mean-centered values divided by the sample size minus 1, and then down below you have the matrix vector product, which are the exact same thing, right? If you do the math, they come out to give you the same exact answer. And so we can think of our variables A and B, or the values of our variables A and B, as lying in some super highly dimensional vector space for those variables, with each axis representing the measurements or the observations for each like one of our values of those variables, right? So for A and B, A1 and B1 would be on this axis here, and then A2 and B2 would be on this axis here, and then there'd be many more as well, right? depending on how large our data is. And so we can put A and B in this graph here. So this red one here is going to be A, and this blue one here, or this green one here, is going to be B. So with these mean-centered values as the coordinates of our variables, or our vectors here, we can then take a dot product between B and A. And no matter how you think of the dot product, as a linear transformation onto the number line, or as a shadow cast between one vector and another scaled by the lengths of the vectors, it doesn't really matter, but it's just a good way of telling you how closely pointed together two vectors are, right? So if B and A are like this, then the dot product would tell you how closely pointed together they are, scaled by the lengths of those vectors. And so this is kind of exactly what the covariance is telling us, right? It's telling us how closely pointed together our variables are, scaled by the values, the mean-centered values of those variables. So you can think of multiple different situations that you might expect, right? So you might expect to see very high covariance in which both vectors, A and B, are pointed very closely together that would lead to a high covariance. And you can think of other situations in which the vectors are perpendicular or almost perpendicular, in which you'd expect to see very low covariance. And of course, for all of this, again, the lengths of these vectors are going to be scaled by the actual mean-centered values. And so this is going to depend on units, right? Like if we're using centimeters to measure A, and then a different day we're using meters to measure A, we're going to get very different values for the covariance between A and B, depending on the units that we use to measure each of our variables. And so it'd be really nice to be able to express this in a kind of unitless way, right? That does not depend on the actual units, maybe in a way that would be scaled by the variance in each of our variables. We can start off by mean centering all of our data, because that's really just what this or this does, is it mean centers your data. So the mean becomes 0. And so that's what this here does. So if I want a mean centered data frame containing all of my data, my I1, I2, and dependent variable D, I can use this handy apply function, which will apply a function given inside of this function over all of the columns of this data frame. So this x here, x, is going to be what I define the data frame as. So in this case, I want it to be the data frame of I1, I2, and D, and these are all going to be column vectors. So this margin equals 2 here becomes important. Because these are column vectors, I want to use the second dimension, I guess. If you want it to be, if you're using row vectors, you use margin equals 1 instead. But since we're using column vectors, it'll be 2. And then we define the function here as well. So the function is going to be defined as the function that takes in an input vector. And then we're going to use these curly brackets to indicate what goes in that function. And it'll return the input vector minus the mean of that input vector. So this will mean center our input vector. So let's just do that real quick. And then we can look at our mean centered data here. And so down here, right, we see that all these middle numbers kind of look like they're around 0. That's certainly not the most accurate way of seeing that your data is mean centered, but as we can see here, we got negative values for when it's less than the mean and positive values for when it's greater than the mean, and that's what the mean centered data here means. So then we can make this mean centered data into a matrix here in R, and so the syntax for this is this as matrix function. Pretty simple to remember, and so we can look at M as well, and it's the exact same, right? It's just stored differently in R itself. And so then we can use this same exact formula that we had above, but modified to take in this matrix as the input instead of just the vector. that we were using previously. So here we have the transpose of this matrix, and we're doing a matrix-matrix product here, and then we're going to divide it by our sample size minus 1. And so then we can have a look at this, and this should be a matrix of the covariances. So here we can see we calculated the covariance for I1 and D before here. So we can look at that and see we have 2.56, and I1 here, I1 and D have the covariance here of 2.56 as well. And so you may notice that this diagonal kind of implies that there's a covariance between I1 and I1, and that's going to be 3.3. But we've already calculated that. The covariance between I1 and I1 is just the variance for I1. And so we can look again at that and see it's also 3.3. So the main diagonal of this covariance matrix is just the variance for each of our variables here. So again, this covariance matrix is equal to the transpose of your data matrix times that data matrix itself divided by your sample size minus 1. And so the people who wrote all the functions for R wrote in this very handy cov function, which calculates a covariance matrix. And so we can use this same data frame here that we defined in our apply function. We can hit enter on that, and it's going to give us the exact same thing, just minus all of this work. And the covariance is great, but it doesn't really tell us everything about the data that we would like to see. So these covariances, they only really tell you like a direction of the effect. So this 2.56, this is positive, so that we know that D and I1 have a positive relationship, right? As I1 increases, so does D. But beyond that, we don't really know, or we can't really tell how closely how close the relationship between these two variables actually is. And so that's where the correlation, as opposed to covariance, comes in handy. And so the correlation here is pretty easy to calculate from the covariance. So if we want to look at the correlation between D and I1, we'll take the covariance from there, and then we'll divide it by the product of the square roots of their respective variances. So for D, that'll be 2.21, and for I was looking at I1 will be square root of 3.3. And so we can hit enter on this and get a correlation, this is a Pearson's correlation, Pearson's product moment correlation of 0.948. And so this 0.948, this value for the Pearson's product moment correlation varies from 0 to 1, with 0 meaning that it has no correlation whatsoever. So if you change your independent variable, your dependent variable, who knows what's going to happen with it. Whereas a correlation of 1 indicates that they are perfectly correlated. So if you increase your independent variable, then you'd expect to see a corresponding output with like 100% certainty, right? You know what's going to happen with that other variable. And so 0.94 is a pretty high correlation. So that tells us that these are two very correlated variables. And so with this correlation, you can also make a correlation matrix, just like we did with the covariance matrix. And the way that that's done is going to involve a little bit more math than the covariance matrix did. And so we're going to start off by generating an empty matrix here. So I'm going to call this vars, and this is going to be populated with the variances from our covariance matrix. And so the matrix function in R can be used to generate matrices from pre-existing vectors. So this data is what you're going to be using to define your vector. And so since we're generating a 3x3 matrix, we're going to need 9 values. And so we're going to want all the values to be 0. We're going to have that 9 times. And then we're defining the number of columns, and since this is a square matrix, also the number of rows to be 3 here. So we'll hit enter and then look at what vars is. And so as you can see here, it's just a matrix of all zeros, a 3x3 matrix of zeros. And so now you can use the handy diag, spelled that wrong, diag function for diagonal in R. And so you can set the diagonal of your vars matrix to be equal to the diagonal for your covariance matrix here. And so if we look at vars again, it'll have these variances on the main diagonal, while the off diagonal values are still going to be 0 because we didn't change them, we just changed the diagonal here. And so then we're going to take the square root of our variances here. And so if you remember from up here, we took the square root of our variances, multiplied them together, and divided this by that product here. So we're just taking the square root of the variances down here. And so as you can see here, it just gave us the square root of our variances. So next, what we're going to do is we're going to get the inverse of this, right? Because if you remember up here, we divided our covariance by the product of our 2 square roots of variances. So we want, if we're going to do a matrix multiplication, we want the inverse of that. And so the easiest way to do this would be to divide 1 by our square root of variances, but this has an issue, right? This has an issue because if we do that, we get these values for infinity because it tries to divide 1 by 0. And so we don't want these. We don't want these inf values. So instead what we're going to do is we're going to use the R solve function. And if we have a look at this, it is the exact same as this, but with zeros instead of the inf values. The matrix inverse here has the property that if you multiply it by the matrix that it was made from or came from, or is the inverse of, it'll just give you the identity matrix. And so that's why, because we have a diagonal matrix, that's why we can divide 1 by this to get the values along the diagonal. And so next what we're going to do is we're going to actually calculate our correlation matrix. So if you remember up here, we have the product of these 2 square roots of the covariances, or the product of the inverse of these 2 square roots of the variances, because we're dividing here. And so what we want to do is we want to multiply this square root variances inverse by our covariance matrix, and then this will give us our correlation matrix here. So if you remember, we had calculated the correlation up here for I guess this is D and I1, and it gave us 0.94. And so you can see here in our correlation matrix, we also have 0.94 for this. This comma 3 is going to be our D, and this 1 comma is going to be our I1. So this will calculate all of the correlations for our covariance matrix. Very handy. So here I'm just going to explain what's actually going on when we calculate the correlation matrix. So to start off with, I have my variables I and D for independent and dependent variable. And then directly underneath that, I have my covariance matrix. So this S sub I squared is going to be the variance in I, and S sub ID squared here is going to be the covariance between I and D. And then right next to it, I have this S equals S, the square root of S squared, And that's just saying that the standard deviation S here is going to be equal to the square root of the variance, which I'm representing with S squared here. So here we have our inverse standard deviation matrix, which we calculated in R earlier. And we have 1 divided by the standard deviation in I up top here, and 1 divided by the standard deviation in D down below here, and then zeros in the off diagonal. And so directly underneath that, you can see the standard sort of calculation for the correlation between I and D. So here we have the correlation of this S squared sub ID, and that's going to, the correlation of that is going to be equal to this S squared sub ID here times the inverse standard deviation in I times the inverse standard deviation in D. Since this is what we're looking for, I'm just going to quickly write out the matrix multiplication that we're going to do and then show you how that contributes or how this creates this solution right here. So here we have our full matrix multiplication written out, and you can see already that this is going to give the answer that we want. So this first row here is going to get multiplied by this first column here, and then subsequently this first row again here. Actually, I'll make this a different color. This first row again here would get multiplied by this first column here. And you'll see that there's a lot of zeros here. So what you're going to end up with is going to be just S squared sub I divided by S sub I times S sub I. And so to illustrate that, I'm just going to do this first matrix multiplication followed by the second here, just so that we can get everything all done up nicely. So this is going to be S sub I squared over S sub I. The second one here is going to be S sub I D squared over S sub I. And then S sub I D squared, S sub D, S sub D squared, S sub D in a matrix. And then we're going to multiply this matrix by this last one here, and that's going to give us, well, a 1, but S sub I squared over S sub I times S sub I, and then S sub I D squared over S sub I times S sub D, and then S sub I D squared over S sub D times, or S sub D times S sub I, and then S sub D squared over S sub D times S sub D. And so you'll see that these elements here along the diagonal are just going to cancel out and become 1. So that's why the main diagonal in the correlation matrix is just 1. And then these off diagonal elements here, you'll see that this is the exact same as the calculation that we did up top here for the correlation. But of course, R has already beaten us to the punch on this as well. And so they've implemented this cov2cor function that'll take a covariance matrix and just return your correlation matrix. So how handy. We don't need to do any of this linear algebra stuff. We can just use this handy little function here. And even more handy is the cor function. So the cor function will take a data frame, and so we had defined our data frame up here as the data frame of I1, I2, and D. So I can just copy that and put this into this cor function. So this just generates the correlation matrix directly from our data frame here. So if I hit enter, I get the exact same thing. So next, if you're familiar with statistical tests, you might be wondering, well, can we actually do a statistical test on this correlation here? And the answer is yes, of course you can. But first, we got to go over the R squared. So this cor gives you these, which are also called the R, right, for the Pearson product moment correlation is abbreviated as R commonly. And so if we set R equals that, and then we do R squared, we get the square of the Pearson product moment correlation, which is commonly reported as a measure of how closely correlated these variables are. So the R squared for I1 and D is 0.89. And this R squared here tells us the proportion of the variance of our dependent variable D that is explained by our independent variable I1. So this 0.89 is 0.89 out of 1 of the variance in D is explained by I1. And so that's pretty handy. That's certainly a more useful measure of the correlation between two variables than anything else that we've seen so far. But you can do a t-test on the R squared or on the R itself. And so the t value for this is defined as the R, right? That's the correlation multiplied by, and this is a element-wise multiplication, not a matrix multiplication. This is just the asterisk on its own is element-wise multiplication. Multiplied by the square root of, this is the sample size minus 2, and this is the degrees of freedom for this t-test, and it's minus 2 because there are two variables that we're looking at here, and then we're dividing it by 1 minus the R squared here. And so if we hit enter on that and then look at t, this gives us t values for each of these comparisons. So of course, here along the main diagonal, they're all infinity because this is just going to be 1 minus 1, and we're dividing something by 1 minus 1, and so that's undefined, and R just defaults to infinity for that. But for all of these off diagonal values, we get actual t values. And so with those t values, we can compare those to our t distribution, which R has a very handy function for as well. And so that's this pt function here. And so we first plop in our quartile, or quantile, sorry, which is going to be negative t. Our degrees of freedom are going to be the same degrees of freedom that we used for the t here, which is this. And we can just hit enter on that, and it spits out our p-values. So if we're using a cutoff of 0.05 and alpha of 0.05, it looks like our I1 and our D would be considered significant, and then it looks like none of the other comparisons would be, or none of the other correlations would be considered significant in this case. But of course, again, R is a statistics programming language, so of course they already have this in there. It's core.test. Will give you all of this, but with a lot less work. And if you want just the p-values for core.test, you can use this $ p-value. If you don't put this $ p-value here, it gives you a very long explanation of it. So here we ran core.test, and we're comparing D and I1, or we're looking at the correlation between D and I1. So this is Pearson's product moment correlation, data D and I1, gives us our t value, as we can see up here. We calculated that here, and it's the same here. Degrees of freedom are 3, that's that length of D minus 2, our sample size minus 2. P-value is 0.01407, and we had calculated that here just with more decimal places here. And it gives us all this other stuff, even a confidence interval and an estimate for the actual correlation or R value down here as well. So let's put that down there, and then put up our p-value, $ p-value here, and this gives us just the p-value. So if that's all you're looking for, that's the way to get it. So what this p-value for core.test tells you is whether or not you have a significant relationship between your two variables that you're looking at. So in this case, since we're looking at D and I1, and our p-value is 0.014, this would be considered to be a significant relationship between D and I1, and therefore we would reject the null hypothesis that D and I1 are not correlated, or that there is no relationship between D and I1, or that if you increase D, I1 will not change, or will change in an unpredictable fashion relative to D. So in this case, we can see, since this p-value is less than 0.05, we can conclude with decent certainty that as you vary D, I1 will be expected to change in a predictable or more or less predictable fashion. So that's all this p-value here tells you. But I'd like to return to this r squared that I had talked about a little bit earlier. So the r squared is called the coefficient of determination, right? And so it tells you the proportion of variance that is explained by, so this one would tell you the proportion of variance in D that is explained by I1. And so the way that we can conceptualize this is kind of like a Venn diagram between I1 and D, right? And so if this r squared is 0, then the Venn diagram would be two totally separate circles. But here we see that it's 0.89. So 0.89 it represents the overlap between these two circles. So before we wrap up, there's a few things to keep in mind here about the covariance and correlation. So the first one is that they test for linear associations in your data, right? So in this case, we have our A and B variables. A is just going to be 1 to 10, B is going to be 2 times A. And then you can just look at, the plot of them, and the correlation of them is just going to be 1 for obvious reasons, right? Because there's nothing going on here, no noise. It's just a simple linear relationship between A and B. And so, of course, you can also add constants to one of these. So say B is going to be 2 times A plus 5. Everything else is going to be the same. And you're going to see it's the same exact thing, right? The correlation is still going to be 1, because we haven't changed the fact that it's just an underlying linear relationship between the two. However, if we were to, instead of doing a linear relationship, do maybe an exponential relationship between A and B, but keeping everything else the same, we can see that the relationship here is changed on our graph, right? So as A goes up, then B does not follow a linear relationship with A, rather it follows an exponential relationship. And so if we look at the correlation here, it's not going to be 1 anymore, even though we haven't introduced any noise. Because this isn't a linear relationship between the two, the correlation hasn't captured that relationship. So this is one thing where you might see log transformations come in. So if we take the log of B, we're just going to get A back out, right? And so if we look at a linear relationship between A and the log of B, so maybe core A and then log of B, we're back to having a correlation of 1. So the last thing that I'd like to talk about here is the multivariate normal distribution and the connection between the covariance matrix and this distribution. So I'm going to be using ggplot instead of the base R plots because these plots from ggplot look a lot better than the base R plots do. So in order to get started here, I'll define a covariance matrix as being 8, 3, 3, 2 here with n row 2, and so then we can have a look at this, and we're going to see that we're going to have a variance in this 1 variable of 8, a variance in this 2 variable of 2, and a covariance between these two variables of 3. So then we can specify a number of samples to take here with this n equals 1000, and then we can put in this call to this mvt norm, our mv norm function, and we can put in our n here, and we can specify a mean for that as well, which we're going to say is 0, 0 to keep things simple. And then for the sigma here, we're going to put in our covariance matrix. So we can put in a call to that. And then we can have a look at our data here sampled from that multivariate normal distribution. And so you can see we have 1,000 entries here in this data frame. As we can see, it's printed out 500 of them and it's omitted another 500. And then we can have a look at what this data actually looks like. So here I have a call to ggplot, specifying the data is going to be our data frame of our X matrix there. with the x-axis being our x1 and the y-axis being our x2. Those are just the names of these columns, right? So x1 is going to be this column on the left, x2 is going to be this column on the right. GeoMPoint is a call to a point or dot graph. So each individual data point is going to be represented by a blue point of size 1. This theme classic makes the graph look a little bit cleaner than it would in base ggplot. And then we can also specify limits, right? So for each axis, we can say it'll span from -10 to +10. Then we can also specify labels, right? So for our title, we can say, okay, we're going to want the covariance and the determinant of our covariance matrix, which I'll talk about shortly. And then we can also call in this variance in x and variance in y for each of those axes as well. The sprintf function here is just a formatted string function. So this %s here is where this will go, right? So if we have covars 1, that's going to be the first entry in our covariance matrix, and it'll go where this %s is here. So we can hit enter on that and have a look at our graph here. And so you can see that we have a positive relationship between x, our x variable, and our y variable here, with much more spread in our x variable, since it has a variance of 8, while our y variable has a variance of 2. We're also going to see a covariance of 3, which means that it is pretty strongly covariate here, or it has a strong covariance. As you increase x, you'll see a corresponding increase in y. So the multivariate normal distribution is specified by this probability density function. And if you take the integral, the definite integral under this function, then you get the probability of seeing a given value for your given inputs, right? So this is a pretty confusing function here. It's got a lot of funny looking notation. If you're not familiar with what these symbols mean, you might have a hard time figuring out what to do with this function. So I'm just going to quickly break down what these different symbols mean. So we'll start off with this top bit, this exponent right up here. So this initially looks to be a matrix exponent, but I'll show in a little bit that it's actually not. So this x here is going to be a vector of your different random variables. So in the two-dimensional case, this would be just like x and y, and then transposed here. So this mu is similarly going to be a vector, but of the means of your random variables. So x bar and y bar. This sigma to the -1 is the inverse covariance matrix. So just the matrix inverse of the covariance matrix. And then this x minus mu over here is the same as it is in front of the inverse covariance matrix. Up here in front of the e, we have 1 divided by 2 pi raised to the k over 2. This k here is just going to be the number of variables. So again, in the two-dimensional case, this would just be 2. And then this e in these bars square rooted is the square root of the determinant of the covariance matrix. The determinant just kind of tells you like the size of a matrix. So since matrices specify linear transformations, then you can take how much that linear transformation scales like an area or a volume, and then that'll tell you like the size, I guess, of a matrix. So through the magic of fast forwarding, I'm going to show you a little bit more about this exponent here and break it down. So here on the left, I've written out our inverse covariance matrix, and I've simplified that down to this just ABCD matrix because I'm lazy. I don't want to write all this out every single time that I have to write any one of these in the future. So here's our first operation. This is the same as this x minus mu transpose times the inverse covariance matrix. I've simplified it down a little bit and just assume that we're using mean-centered data already. So otherwise it would be like x minus x bar and then y minus y bar in there. And then down here we have the second operation. This is multiplying this by this second vector. And so then you can see at the bottom here we have our exponent that is just a function of our x and y coordinates. Again, assuming the two-dimensional case. If it was 3 dimensions, there'd be a few more terms here. Right, so this is great, but what does this mean? What does this actually tell us? So a good way to think about this is to just draw it out graphically. So again, assuming that we're working in 2 dimensions here, we'd be dealing with normal distributions, Gaussian distributions over each of our axes here. And we can think about what our probability density is going to look like as a sort of function of what our covariance matrix looks like. So if we have a covariance matrix that has really low variances in both variables, we'd expect to see a really narrow probability distribution that looks kind of like that, right? Like there wouldn't be a whole lot of points out here. It would be mostly contained within this little area right there. Similarly, if we can think about what it would look like if we have high variances in one variable, or maybe in both variables, right? So in one variable, it might look something like this or like this. And then if you have high variances in both variables, it might look something like this. Similarly, the covariance itself between these two variables will tell you how sort of skewed along the diagonal here your data is going to be, or your probability distribution is going to be. So if you have a high covariance, it's going to look something like that, a high positive covariance. Similarly, if you have a negative covariance, it will probably look something like that. The determinant of the covariance matrix kind of specifies like how big, how spread out in all of these dimensions your data is going to be. So if you have a high determinant of the covariance matrix, you have like a very large spread of your data. And if you have a very low determinant of your covariance matrix, it'll be a little bit more contained